right, let me now introduce my next speaker, which is Mr. Larry Wetzel. And Larry has a really interesting background and career. Started his career in construction, 18 years in construction. Then founded a company called Clean Room Technologies, which he built up really from scratch and sold it then to a French company, which he then went on and worked for a few years. Went on to then working venture capital and helping other companies get started. I guess, although I didn't ask him this question, it then sounded like he wanted to do that same thing again himself, because in 1996 he started a company which later became the name it has today, which is Air Innovations. You know, working in the area of, so broadly, indoor air quality, and he's been doing it with this company since that time. You know, currently, he is the, I guess, chairman of the board of the company, and your son is the president, I believe. That's correct. So it's a wonderful, really nice and interesting company that I think we're going to hear something about. Larry has degrees in math and engineering from Penn State, so I like that because I have degrees in math and engineering. So that was I like that common point. And he has 8 patents, so I think that's a really fascinating background. So with that, I will turn it over to you.
Thank you, Eric. You switch slides with this too?
Yes.
Okay.
Arrow keys here.
All right, good afternoon, everyone. Thank you for attending on this very humid day outside. I'm going to attack the indoor air quality from a little bit different perspective. It's going to be more on a balance, the idea of a balance between the energy utilization and the health aspects of it. No, that didn't work. There we go. Okay. Indoor air quality. And I think it's well known that it does affect human health, obviously comfort, and a lot has to do with economics also. The thing about indoor air quality is it's often identified by what it isn't than what it is. And so indoor air quality, good indoor air quality could be defined as it doesn't cause discomfort to its human occupants. It doesn't cause adverse health effects. And it doesn't cause degradation of property. And that's actually a very important aspect, especially of the humidity, as we'll see later on. Now, the primary parameters of indoor air are obviously temperature, humidity, and airborne pollutants or contaminants, however you want to identify them. They probably could just be dust or dirt, wherever you want, except that they're defined by their effect essentially on human beings. So that's why they were called pollutants or contaminants. Pollutants include particulates and gases. And the particulates include viable and non-viable, large and small sizes. And the smaller the particle size, the longer it will stay in suspension, and the further into the human body it will penetrate. So the very small particles are the ones that we often overlook, and yet they're the ones that cause the biggest problem. Gases, such as CO2, VOCs, formaldehyde, exist in all aspects of indoor air and some outdoor air. And the adverse effects of health include the incidence and severity of upper respiratory diseases or illnesses such as asthma, multiple chemical sensitivities, COPD, etc. These are all very well documented and known. So what we're looking at is indoor air quality. Now, temperature and humidity, which are the two first parameters I put up there, they're pretty well universally known. Obviously, you can sense temperature change. And for a very inexpensive amount, you can have a thermometer or a thermostat. So they're very broadly known. And everybody kind of knows that they like it somewhere between 65 and 75 degrees. But high or low temperatures can cause discomfort and even adverse health effects. So on certain sensitive individuals, a high temperature or a low temperature can have an impact. High or low humidity can also cause discomfort, obviously, and adverse health effects. The thing about humidity is also there's going to be the degradation of personal property and the promulgation of additional pollutants. As an example, high humidity promotes mold growth, insect infestation, rotting of wood, warping of furniture, peeling of paint and wallpaper, etc., etc., etc. And also even the degradation of insulating values in some of the insulation that's used. So this following slide is one of my favorites. Shows the impact of relative humidity on air quality. And as you can see, the optimum zone in this 40 to 60% range. You get below that or above that, and you have an effect on viruses, bacteria. High humidity is fungi, mites like it, nice and humid. Respiratory infections, low humidity will affect. Ozone, they're all in the outskirts of high or low relative humidity. So the idea, of course, from a human standpoint, is to stay somewhere in that middle zone. Now, the unintended consequences, I think, of the energy crisis of the 70s, and we increased all of these standards for thermal efficiency, is that we've reduced infiltration in order to improve thermal efficiency. But in so doing, we have actually made the houses, where we spend most of our time, almost small gas chambers, because we've trapped all those pollutants inside of the structure. Airborne pollutants cause discomfort as well as adverse effects, as we saw high and low humidity does. Same with gases. Now gases, of course, will come from many sources, natural and man-made. There probably isn't a piece of furniture today that isn't made with some amount of formaldehyde or some VOCs in it. And of course, this is the air that we breathe. Also in a building, sources of pollutants include combustion sources, building materials and furnishing, household cleaning, disinfecting products, personal care products, and outdoor sources are all sources of pollutants. Now, this is one of my favorite slides. This goes way back, 73, something like that. No, here it is, 84. There it is. Anyway, what this shows very nicely is a relationship between particle sizes, quantity of those particle sizes, and the rates at which they settle. And here's some of the types of impurities that are in that size range. So if you're looking at fumes, dust, fog, they're all kind of idealized here. Human hair would be somewhere in that 50 micron size. What's interesting is the settling rate. You'll see it starts out in feet per minute, and then it goes down to inches per hour, and then 1.4 inches per hour, then 3/64 inch per hour. And so obviously these smaller particles are going to stay in suspension for a very long time. And the number that are contained in an cubic foot of atmospheric dust, the numbers are in the millions. But what's also important is the surface area, because the surface area is where the particles can have or contain the bacteria, the viruses, and can do the most damage in terms of it adhering to something. So the surface area of a large particle is actually relatively small compared to the number of small particles. And from the standpoint of dealing with particles in air, the settling rate is important, but also you see when you get down below this 0.1 micron size, the particles move like a gas molecule, according to the Brownian laws. So they're very, very difficult to behave or get them to behave in an air system. Now, some of the solutions, temperature and humidity are relatively controlled, thanks to people like Carrier, with heating, cooling, and humidification equipment. But airborne particulates are not as well known. One of the reasons, of course, because you can't see them. Because you remember the particle size is here, you're not going to be able to see anything less than it's about 100 microns, it's about a human hair. You won't be able to see any of these floating around in the air. And so you can't see them, you can't necessarily feel them, and the instrumentation that it takes to detect them and quantify them is very expensive. So this is an area that I've often said is an area for research, is in low-cost pollutant sensors. The EPA and Department of Energy published numerous articles on it, some of their findings. I mean, I think we hear this all the time. People spend as much as 90% of their time indoors. And they have reached a conclusion, indoor air quality is now considered worse than outdoor air quality. And I think a lot of that, of course, comes from the increase in the energy efficiency of the houses at the detriment of probably human health. Now, the EPA's recommended primary strategies for improving indoor air are source control, to eliminate it at the source. Obviously, if you can eliminate particles, if you can eliminate the gases, that's the best thing to do. Improve ventilation, so that you can dilute and reduce the particles and the gases. And the third is utilization of air cleaners for entrapment and neutralization. Now, you would think source control might seem obvious, but it's not that obvious, and it's very difficult because they are so pervasive throughout everyday life. I mean, we're all in here in this room, and we're breathing this air, and we're exhaling our own, and the building materials are letting off outgassing. There may be combustion in a home, a lot of combustion gases, particles, and the cooking that you're doing is coming off the stove. Showers, animals, and even natural, such as radon, is an obvious pollutant. And air cleaners are used to remove particles and some gases. They're available in portable units for single rooms, and they're available large sizes in your furnace for the whole house application. They can be safe and effective, but they do require to be properly maintained, and they have a not insignificant lifestyle cost to them. So the primary purpose of this discussion was on ventilation and pressurization as a means of helping to control and improve indoor air quality. And the ventilation is primarily the use of outside air to dilute and purge pollutants in the indoor air. So again, it can be applied to single room or to whole house. I mean, the slides that Eric showed apply to a whole house application. I'll show it a slide for an application for a single room. But the ventilation is absolutely important for controlling the pollutants in the air and for controlling actually humidity. It can be a very important tool for controlling humidity. So along with ventilation generally comes what I call a sidekick, and that's pressurization. And pressurization results from the balance or imbalance between the ventilation, exhaust, and intake. So the slides that Eric had shown, he showed some intake, but then he shows, of course, some exhaust. So the question is, what happens if there's an imbalance, and do we want to have an imbalance? Now, we have many examples today where we use pressurization to control indoor air quality. And as an example, hospital rooms, especially in the operating room or in the isolation rooms, where we actually create a positive or negative pressure in that room relative to an adjacent space. The purpose, of course, is so that there's this flow, outward flow of air, which can contain the pollutants, if in fact we're trying to protect the patient in that room. If that patient is got some kind of a communicable disease, then we want it to be the opposite way. We don't want their stuff to get out, so we go to a negative pressure room. The manufacturing of pharmaceuticals and medical devices are all done in clean rooms, and one of the major techniques in clean rooms is the pressurization between spaces. Biological safety laboratories prevent the escape of airborne biological and chemical agents. Now what we're talking about here is pressure differentials of like 0.05 inches, 0.1 inches. Gives you a relative idea. The carrier dome, the roof starts to lift at about 0.4 of an inch and gets fully inflated about 0.8 of an inch. So you're talking about, and when you go through those doors, you know there's a lot of pressure in there. But you also know that that air is flowing out of there pretty fast. So if you reduce that to where you're somewhere around 0.05 or 0.10, you'll still get this outward flow, except you can still open the doors. Okay, so if we think about those hospital rooms, the same principle could be used in homes to control the direction of airborne contaminants, with the cleanest air being supplied to where people spend most of their time. And most people spend most of their time in a bedroom, about a third of the time. And so if there was a way to have that air, the cleanest air, enter into the bedrooms and then flow through the rest of the house and exhaust out the normal kitchens or toilet rooms, we could probably improve the indoor air quality of a bedroom substantially. Historically, generally speaking, we relied on HVAC systems to supply the air we breathe and control the quality. However, as I mentioned before, this is becoming more and more of a problem because we have more and more contaminants in the air. Or maybe we're just learning more about those contaminants. But in any case, it is a factor. The use of high-efficiency filters can reduce the number of airborne particles, but again, as Eric pointed out, the system has to be running. If your system is cycling on and off, half the time it's not running, you're getting no benefit of the filtration or the humidification. There are chemical filters, charcoal filters, again, that can reduce the gaseous contamination, but again, it's at a high cost. One, because of the cost of the filter, two, the maintenance, but three, because you don't even know when the filter is saturated. It's not like a particular filter where you can see the dust or dirt. You can't see it on a charcoal filter. But also, not all individuals are susceptible to airborne contaminants, and this is a bit of a problem. So when we attack the whole house, in many cases, it's only one person in the house who's really sensitized or sensitive to it. So it's kind of like throwing everything at one problem. And when we talk about energy and the cost of energy, if we could just focus in on what is really the important outlook, then maybe we could accomplish that. So I think that's an important consideration, is that when you're dealing with a whole house, you're always dealing with the entire structure, whereas what you're really trying to do is help the indoor air quality for an individual. EPA and NYSERDA have collaborated on a homeowner's guide to ventilation. And here, it's just an illustration that shows the amount of exhaust, kitchen exhaust, toilet exhaust, through the stack, the clothes dryer. So in this house, unless you have some source of air coming in, which there isn't, it's going to run at a negative pressure. And the negative pressure, of course, is like this, which then sucks in all of these outdoor air pollutants, which EPA now says is more contaminated. The indoor air is more contaminated than the outdoor air. But this won't work in a newer structure where the rooms are so tight, or the buildings are so tight, that you don't get actual ventilation, and then you also lose control of your humidity and your temperature. On the other side, if you have a positive pressure, if you can control what's coming in and going through this house, then in fact you can keep other pollutants out as long as you can control what's coming in. So they talk here about general ventilation to dilute the pollutants from sources that exist in many locations, or they talk about spot ventilation. And so spot ventilation would be maybe one area inside the house. So, by maintaining the house at a slight positive pressure, we can keep many of the outdoor pollutants from entering through the cracks and crevices. And of course, as the houses have gotten tighter and tighter, this becomes more and more feasible. It will even work in some of the older houses, except if you want to maintain some kind of relative pressurization, then it would take more ventilation. However, to do that in a 2,500 square foot home, average 8-foot high ceiling, is really a challenge to maintain pressurization, even in a very tight house. A more practical approach might be to use techniques used in hospitals, industrial clean rooms, where the pressure differential is maintained between spaces. Again, the idea is that there's not much you're going to be able to do about the kitchen because you're going to have all of these pollutants there, people are running in and out. But if you can maintain a clean bedroom, then people can get at least 8 hours of relief from whatever they're sensitized to. So the positive pressure is obviously driven by more air being supplied to the space than what is exhausted. Also, then, if this air that's being supplied to this cleaner room is also composed of a higher percentage of fresh outside air, then in fact you can have more air to dilute the concentration of pollutants in that room and exhaust them out through the doors and through the exhaust in the house, which is the bathroom exhaust and the kitchen exhaust. So this is just a slide from state of Connecticut saying a healthy home is well ventilated, bringing fresh air into the home helps prevent, remove and dilute these chemicals and make breathing easier. You'll probably find thousands of these on normal website. So now, what might we do? And I'm just going to show a potential unit that was developed by us. Carrier got their name in writing, so I'll get ours in writing. So Air Innovations manufactured a unit called Heparis, which actually was developed through a lot of grants and work with the Center of Excellence. But this is an example of a device that could be used, is used for ventilating and pressurization control in a room in a house. The concept is that it has a heating and cooling, so it can take over control for temperature and humidity in the space, which means that you can isolate that room essentially from the rest of the house. You can bring in fresh outside air through an air-to-air heat exchanger, as Eric was talking about, HRVs, and you exhaust a certain amount of air. So as the unit is running, and this unit is designed to run at multiple speeds, which means you can then keep it running all the time, so it's working for you the whole time, at least while you're in the space. There's high HEPA filters here, and there's also the ability of charcoal and even ultraviolet if in fact that's what the individual is sensitized to. So you really create a mini environment in the bedroom for the occupant. And the outside air comes in, goes through the heat exchanger where it exchanges heat with the air that's being exhausted. It then enters the unit, and all of the outside air goes through the HEPA filter before it goes to the space. And here you're talking about air changes in the room for ventilation of between 1 and 1.5 air changes per hour. And here you're talking about 8 to 10 to 12 air changes per hour in the recirculating space. So here's where you have the ability to trap all of your airborne particulate contaminants primarily, but through the exhaust air you also have the ability to exhaust not only particulates but then also gases. And so therefore you have the ability to purge the space of gaseous contaminants. But as I said, all the outside air, which is an important consideration because there are many types of outdoor heat exchangers that fit in a window, they do not filter the air, and so you can bring in a certain amount of pollen and things like that that people can really be sensitized to. So this is an example of a way to maintain a high level of indoor air quality in a particular room within a house, maintain it by pressurization and temperature humidity control. Thank you.
Any questions?
So Larry, so you've got an HRV or an ERV? So it's just
the unit that we have in that right now is an ERV, and the reason is because I can get 85% efficiency thermally, sensible.
And
but in ERV, most of the ERVs, you end up giving up sensible heat recovery in order to get some moisture recovery.
yeah.
So, I mean, we can put it in there. We're talking about 30 CFM. And so there are very few people that make that small energy recovery.
So it has to be imbalanced. So it has to be imbalanced to provide pressurization. So how much is it in?
We're bringing in.
What's the
we're bringing in
imbalance?
somewhere in the range of, depending on how the filters are, 30 to 35. We're exhausting 25.
Okay.
So you have about 10 CFM delta.
And so I guess one, so of course the imbalance hurts the efficiency of the heat exchange.
Yes.
But you think it's still worth doing the heat exchange?
It's a matter of energy, cost of energy versus cost of healthcare. You tell me.
Well, I mean, but if you just cared about healthcare, you could just have imbalanced flow and no heat exchange.
You could, yes. And so the question is, on an improved version of this, would we actually have a room sensor that would control the speed of those fans? Yes, you could do that. It's a matter of, again, cost and sophistication. So
Yeah.
you could maintain, you could run it so you could maintain a negative pressure if you wanted.
And I guess so if you do this, so you've got a heat exchanger, you add sort of bigger fans to get through the heat exchanger, there's an energy penalty of
Right.
that, and you have a degraded heat transfer. So I guess, so you could serve your function and not do the heat exchange, and I was wondering if you think there is still an energy benefit of having the heat exchanger. So.
Oh, I think that there is, because if you're talking about running this 24/7,
Okay.
and you're trying to purge the space, you're only talking about 1 to 1.5 air changes per hour. You really need to keep the unit running in order to do it. You can slow down the main recirculating fan, and you can actually shut this off if you want to. I mean, our unit has a switch on it for shutting it off. You're going to go out and wait for vacation and stuff like that. But we do recommend that you run the ERV all the time that the room is occupied.